Hello and welcome to this lecture. In this lecture, we are going to talk about a polynomial. So far we talked about quadratic equations, and a quadratic equation was basically a second degree polynomial, right? F of x, ax squared plus bx plus c. Now we want to generalize this, and if you recall, I mentioned that the term in the form of x to some integer power in general constitutes a polynomial, and we said that the term that has the maximum power, maximum exponent, is called the leading term. Okay, leading term. And typically we order the polynomial in terms either in terms of the from the highest degree to the lowest degree, or from to the lowest degree, which is 0, to the highest degree m. So the highest degree is called the degree of the polynomial p or f or whatever. So the main and basic theorem in polynomials is the division theorem. How do we divide polynomials? Theorem: if p of x and q of x are two polynomials such that the degree of p is greater than the degree of q, and then there are unique polynomials capital Q and R such that our px is q times the capital Q plus R. And the main property here, the main property is the second one. So the second one is the main property of the division. And basically that says that the degree of R of x should be less than the degree of Q of x. Okay? If the degree is equal, we can continue to division with further steps, right? So we go as far as until we get to the fact that the remaining polynomial R of x has a smaller degree than Q of x. In this case, the capital Q is called the quotient of the division, and R of x is called the remainder. Exactly like the way we divide, for example, integer numbers. So if I divide 21 by 2, I get 10 here, 20, and 1. And the division continues until the remainder R is less than the Q, right? The number. So 21 is my P, 2 is my Q, capital Q, the quotient is 10, and the remainder is 1. And the remainder should always be less than the Q, right? Otherwise, we can continue the division further. And because polynomials of degree 0, if the degree is 0, the polynomial becomes a number. Obviously, we see that the division of polynomials is extending or expanding the division of the integer numbers. In the special case, if R of x is 0 or the remainder is 0, we say that px is divisible or can be divided by qx without any remainder, can be completely divided by q of x. And q of x, the small q, or the capital Q, both of them are factors of p of x. The same with numbers. So if I write 21 equals to 3 times 7, we call that the 3 and 7 are factors of 21. And the main property of factor is that when you divide the number by its factor, the remainder is always 0. Okay? That's why when we talk about polynomials, we talked about the factorization. And later on, we will see that any polynomial can be factorized in complex numbers, because any polynomial can be factorized in terms of its complex roots. And we already discussed this in quadratic, right? We said that if you have ax squared plus bx plus c, and we said that if you have two real roots, you can factor it in terms of x minus x1, x minus x2, such that x1 and x2 were the roots. And we can, but there we assume that x1 and x2 are real numbers. Now this can be easily extended to complex numbers. So any polynomial can always be factorized. How to perform a polynomial division? So P and Q, you put them in the standard form. A standard form usually means that you order them from the greatest degree or the highest degree, xn minus 1, etc., and then start the division. But usually the standard form also implies that the leading term has a coefficient of 1. But here I'm going to use that interchangeably. So when I say a standard form, I just mean order the polynomial in terms of from the highest degree to the lowest, highest to the smallest or lowest. Okay, it's an ordered polynomial in the standard form. Step 2, divide first term of px by the first term of qx. Then subtract the multiplication of this term to the q from px. All right, perform part 2 repeatedly until the degree of remainder becomes less than q. Remember, the division ends when the degree of the remainder is less than the degree of q, right? Let's make an example. So let's assume that p of x is x3 plus 2 and q of x is x plus 1. So these are already in the standard form from the highest degree to the lowest, from the highest to the lowest. And we want to perform this division. x3 plus 2 divided by x plus 1. So we take the first term that has the highest degree and divide it by the first term of q that has the highest degree. And we end up with x2. And then multiply this, excuse me, back by the q. So x2 multiplied by x gives me x cubed. x2 multiplied by 1 gives me x2, right? And then subtract this from the original polynomial. And I end up with minus x squared plus 2, okay? And the degree of the remainder still is greater than the degree of the q. So I take this term and divided by the first term, I end up with minus x, and then again multiply back, minus x squared minus x, and then subtract, I end up with x plus 2. The degree is still equal, so one more division plus 1, and then multiply back, x plus 1, and then subtract 1. Now the degree here is 0, which is less than the degree of x plus 1, which was 1. Therefore, this is the end of the division. So we say that p of x is equal to q of x, which was x plus 1 times x2 minus x plus 1, plus the remainder is a number 1 of a polynomial of degree 0. Okay? So order them and divide term by term, the highest degree terms, and subtract until you get a degree less than the q of x. Okay? All right, there is an important point here. Assume that q of a is a real number. Assume that a is a number and q of a is 0. Basically, a is a root of q, right? Q of x. Whenever q of some number becomes 0, basically if we solve q of x equals 0, the solutions are the roots of this polynomial. So if a is a root of q of x, and recall the division, p of x is q of x, capital Q plus r. And remember, this is an identity, which means this is true for any x, any real number or any number. Could be real or complex, doesn't matter. Right now, we're just focusing on real numbers though. This is an identity, which means it holds true for every number x, even complex numbers, okay? Now what happens if we substitute a? Remember, a was a root of q, therefore this term becomes 0, and p of a becomes r of a. So this is interesting, such that we can evaluate the excuse me, we can evaluate the remainder at the roots of the q without calculating the remainder, right? we're not calculating r of x, but we already know that r of a should be equal to p of a, and p is given. So this is a shortcut, and later on this becomes very important in a special case when r of x is actually of degree 0, because when it's degree 0 it means it's a real number, it's just a number, and the number doesn't change. So if we evaluate it in one of the roots of q, we can find a remainder very easily. Alright, question 58. If the remainder of the division of p of x, 2x to the 4 plus mx plus 2, by x plus 1 is 2, what is the remainder of px on x minus 1? Excuse me. And this is exactly what I talked about. When our qx has a degree 1, remember the remainder should have a degree less than q, less than 1, and the degree is an integer number greater than or equal to 0. Therefore, the only possibility is that the degree of remainder, degree of r of x is 0, which means r of x, the remainder, should be a real number. Okay? So let's call this p of x equal q of x times, and we already know what the q of x is in the first division, x plus 1 times some capital Q plus some remainder which is constant. And if I evaluate p at x negative 1, this term becomes 0, and this gives me exactly the remainder, right? So I already know that the remainder of the first division is when I plug minus 1 into the x. So 2 minus m plus 2, which is 4 minus m, which is 2. Remainder is given as 2. Therefore, m is 2. So we already find the unknown here. And then now that we found the unknown m of x, we found the m. Now we go and continue with performing the next division. P of x is x minus 1 times some q bar or whatever plus r bar, some other real number. And again, if I evaluate p at the root of q x minus 1, which is 1, so p of 1 should be r bar, and p of 1 is 2 plus m plus 2, which is 4 plus m, and m was 2, we end up with 6. So the last choice. Okay? Using the previous point, we can make a rule for dividing by first order polynomials x minus some number. Why? Because we already know the remainder. The remainder is always evaluate p at the root of x minus a, which is a, right? And remainder should have a degree of 0. A 0 degree polynomial is basically a real number, a constant. Division by x minus a. Here q of x is x minus a, and obviously q of small a is 0, so a is a root, very obvious. Therefore p of x is x minus a times the quotient plus r, but r of x is a real number, is a constant, it doesn't depend on x. And this is exactly what I said. Degree of r of x, degree of any polynomial should be 0 or an integer number, a positive integer or 0. And degree of x minus a is 1. So 1. So therefore the only possibility for degree of r of x is 0. So r of x is a real a constant number. I mean, in general it could be a complex number, but right now we're assuming that it's a real number. Okay? So we discovered that the remainder is a constant number. The question is how to find it. Again, evaluate the given polynomial p of x at x equals a, which was the root of q of x, and therefore r is p of a. Show that x minus, and this is especially helpful for finding the factors. Why? Because as I mentioned before, a polynomial q of x is a factor of p of x if the remainder is 0. Okay? So a first degree polynomial, the remainder should be a constant number. So we just evaluate the p of x at the root of that first degree polynomial and see whether or not it's 0. And question 59 is exactly this point. Assume that q of x equals x minus 2 is given. And then we have the polynomial p of x, x cubed plus 2x2 minus 5x minus 6. Let's see if q of x is a factor of p of x. Factor of p of x. If it's a factor, then this should be some qx times some capital Q, and the remainder should be 0. That's the point here. So is this really true? Since the q of x is a first degree, the remainder should be a constant number r. And it's actually p of x at x equals 2, which is the root of q of x, okay? Alright, so we plug back in the p of x, x equal to 8 minus or plus 8 minus 10 minus 6, which is 0. Yes. And then if x minus 2 is a factor of p of x, how do we find the other factor? Well, the straightforward way is to make a division, but we can be a little bit clever and try to come up with some smart factorization term by term. We already know that x minus 2 is a factor, right? So how do I take out x minus 2 here? Let's see. So I have x3 minus 8 plus 2x x2 2x2 minus 5x plus 2, right? And obviously the first term gives me a x minus 2, x2 plus 2x plus 4, and then the second term, what does it give me? Let's see if the 2 is the roots. 8 to, yes, the 2 is, so it has to also give me another x minus 2, and if I factor out x minus 2, it gives me a 2x squared minus 4x and minus 1, okay? And then we end up with x minus 2 and the sum of the other two, x squared plus 4x plus 3. And if we do the multiplication, we see that it is indeed true, right? X cubed 4x squared minus 2x squared is give me 2x squared. 3x minus 8x gives me minus 5x, and minus 2 times 3 gives me minus 6, okay? So what are the consequences of the fact that we know how to find a constant remainder? If the remainder of f of x on x minus a and x minus b are r1 and r2, and they have to be constant, then the remainder of f of x on x minus a times x minus b. Now the degree of q of x, what is it? It's 2. So the remainder r of x should have a degree of 1, right? So it should be in the form of m of x, m times x plus n. Two unknowns. Okay? However, because we already know the remainder of f on x minus a separately and x minus b separately, we can look at it this way. Now if I evaluate f at a, again, this x minus a times x minus b is still 0, right? So it becomes equal to the evaluation of r of x at a, which is ma plus n. However, the evaluation of f at a is the first remainder, r of a. The same situation here, f of b is equal to the r of x at x equal b, and that's actually the remainder of the dividing f of x by x minus b, right? So this comes from the equality of f of a equals r1 comes from dividing by x minus a, and the equality of f of b equals r2 comes from dividing by x minus b. And now we have to two linear equations, two unknowns, mn, and we can find them, and it's very easy to solve. Let's just solve it. Subtract the two, m a minus b equals r1 minus r2. Therefore, m is r1 minus r2 a minus b. And the nice form is here. R1 was f of a minus f of b divided by a minus b. Very nice form to remember. Okay? And what is n? N is r1 minus m times a. R1 minus r1a minus r2a divided by a minus b. R1a cancels out. R1b plus R2a divided by a minus b. Therefore, n is a f of b plus b f of a divided by a minus b. This is also a nice form that we can remember. So it's better to remember this. Okay? Question 60. If the remainder of f of x on x minus 5 is 3, this immediately tells us f of 5 is 3. Okay? And on x plus 3 is minus 13. This immediately tells us f of minus 3 is minus 13. Remember, the root here, the root is minus 3, and the root here is 5, plus 5. And we have to evaluate f of x at the root. Then find the remainder of f of x on x minus 5, x plus 3. Because the degree here is 2, the remainder has to have a degree of 1 or 0. So in general, it has to be mx plus n. And we already know what mx is. F of 5 minus f5 negative 3 divided by 5 minus negative 3. 5 minus negative 3. 1 over 8. F of 5 is 3. F of minus 3 is minus 13. 16 over 8 is 2. So m is 2. Right? 2 minus 2. So either choice 1 or choice 4. So what is the second term? What is n? N is 1 over 8 times 5 times fb plus b minus 3 times fa 3. So n is 1 over 8 minus 65 minus 9 minus 72 divided by 8. Let's see, did we make a mistake here? In the original thing, yes. So n, there was a minus sign that we forgot. So it becomes r2 times a minus r1 times b divided by a minus b. And r2 was f of b. So we end up with a f of b minus b f of a. However, I guess in order to not make a mistake, it's better to just go ahead and evaluate this. So what is f of 5? Obviously it's r of 5, right? R of 5, which is 5m plus n, which is 10 plus n. So 10 plus n is equal to f of 5, which is 3. So n is negative 7. So our remainder, without knowing what the f of x was, this is very interesting, is 2x minus 7. Okay? Question 61. Find the remainder of x5 minus 4x4 plus 2x3 plus x2 minus x plus 1 on x2 plus 1. Alright, this is interesting. So x2 minus 1 does not have any real root. Does not have real roots. Okay? But again, as I mentioned, polynomials, and this theorem that we just mentioned for calculating the root extends to complex number, and we already know that the x2 plus 1 equals 0 has two complex roots, plus minus j or plus minus square root of negative 1. But I don't want to go into that. Instead, I want to use this shortcut. Whatever x is, even if a complex number, if I put qx equals 0, the roots must satisfy this equation that when I take the roots and square them, it gives me negative 1. Okay? So if I plug this back into the original p of x, so I calculate p of x such that whenever I have x squared, I put negative 1. And that should give me a remainder. Why? Let's have a look. x5 is x times x4. x4 is x2 to the second power. Minus 4 minus 1 to the second power plus 2x negative 2x times x squared, which is negative 1. X squared is negative 1 minus x plus 1. Right? The only terms that remain are the either x to the first power or x to the 0th power. So I immediately get the remainder. So r of x is x minus 4 minus 2x minus 1 minus x plus 1. So r of x is, we have 1 cancel out, x cancel out, we end up minus 2x minus 4. Okay, so this should be our remainder. Now we can actually go ahead and do the division. It's a tedious division, but the question just asks us for the remainder, and we can always use this trick that x squared plus 1 doesn't have a real root, but whatever root it has, when I square that, it should become negative 1, right? So where in the original p of x, wherever you have x squared, you put negative 1. So x5 becomes x. Okay? x4 becomes 1. x3 becomes negative x. And x2 becomes negative 1. And then we had minus x plus 1. Okay? Question 62. Find the remainder of x plus 1, x plus 2, x plus 3, x plus 4 plus 2x plus 7 divide on x2 plus 5x plus 3. This is interesting. So first of all, this x2 plus 5x plus 3 is our q of x. Therefore, it has the degree of q of x is 2. So the remainder has to have a first degree. So the general form of the remainder should be mx plus n, right? This is our remainder. Now again, what are the roots of q of x? So it's a quadratic equation. Delta is b squared 25 minus 4ac 12 is 113. So the roots are not very nice. I can write them down. Minus 5 plus minus equals 13 divided by 2, right? 25 minus 12. But now we can proceed with the previous approach to find the remainder, right? Find m and n, evaluate this p of x at minus 5 plus square root of 13 divided by 2, and also evaluate it at negative 5 minus square root of 13 over 2. Okay? But we can use a trick here. And this is not a general trick, but it applies here. So let's have a look at the form of x plus 1, x plus 4 times x plus 2, x plus 3, right? Now, why did I factorize this in this way? Because when I multiply x plus 1 times x plus 4, it gives me x2, okay, plus 5x plus 4, okay? And if I multiply the second part, it's x2 plus 5x plus 6. Now you see that both of them give me a term of x to the second plus 5x. And that was exactly what appeared here, right? So if I want to find r of x, basically I have to check the two roots of the q of x. But the two roots satisfy the equation that x2 plus 5x should be negative 3. Okay? So if I put this back in the p of x, therefore the remainder becomes basically minus 3 plus 4 minus 3 plus 6. Okay? And it becomes 1 times 3. 3. So the remainder is actually 3. And in order to see that, I can write p of x. The first term is q of x plus 1, right? The second term is q of x plus 3. And this becomes q of x times q of x, or maybe just factor out 1 q of x out, and it's q of x plus 3, 4 plus 3, and this is our capital Q, the quotient. So the remainder is a constant number here, which is 3. We just immediately found it, and we also found the quotient. So you take q of x, add 4 to it, and it becomes the quotient. So this was a shortcut, and just works for this particular question, but it's interesting to know. Let's do the following question. Question 63. Perform the division of p of x, x to the 4 plus 2 x to the 2 minus x plus 4 on x minus 2, and find the quotient and remainder, and check the relation p of 2 is equal to r. First of all, how do we find r? R is just, based on our theorem, is just p of 2. 16 plus 8 minus 2 plus 4, right? Should be 26. And we can go ahead and do the division and double check that this is actually true. Let's see. I'm going to write it here. X to the 4 plus 2x to the 2 minus x plus 4 divided by x minus 2. Again, order the polynomials, divide the highest order to the highest order, x cubed, x4 minus 2x3, and then subtract. I end up with minus 2x cubed plus 2x2 minus x plus 4, and the second term is gives me a minus 2x2 minus 2x3 plus, remember we're subtracting, right? Minus 2x3 plus 4x2, and then again we're subtracting, so minus 2x2 minus x plus 4, and again there is a negative 2x, and minus 2x2 plus 4x, and again we're subtracting. It becomes minus 5x plus 4, and then divide this by x, minus 5e here, and minus 5x plus 10, and then we end up with negative 6. Did we make a mistake somewhere? So p of 2, 16, so the remainder should be 26. Let's see, x4, 2x2 minus x plus 4 divided by x minus 2. So x cubed x4 minus 2x cubed. Yeah, so this, yeah, we made a mistake here. Let me start from the beginning. Alright, the first term x cubed and then x4 minus 2x cubed. And then remember we're subtracting, so plus 2x cubed plus 2x2 minus x plus 4. And then we end up with 2x2, 2x cubed minus 4x2. And then we end up with 6x2, 6x2 minus x plus 4. We end up with plus 6x here, 6x2 minus 12x. We end up with 11x, right? Plus 4, and then here we put 11x minus 22. Remember, we're always subtracting. Just make sure we don't forget that. We end up with plus 26, right? So this is our remainder, and our quotient is x cubed plus 2x2 plus 6x plus 11. Okay, now I mean important special cases are when we're dividing x to the n plus or minus a to the n by x plus or minus a. So x to the n minus a to the n divided by x minus a. So x minus a divides xn minus a to the n, because if I evaluate p of x at x equals a is a to the n minus a to the n, 0. And remember, the remainder here should be a real number, a polynomial of 0 degree, right? So x minus a divides x to the n minus a to the n. And for any n, doesn't matter. How about x plus a? So again, the remainder should be a number, and that number equals to p evaluated at the root. And remember, the root here is x equals negative a. So p negative a is negative a to the n minus a to the n, which is a to the n times minus 1 to the n minus 1. And this is only true when n is an even number. Okay, so n only even. And we've seen the special case here. So if n is 2, x2 minus a2 is x minus a, x plus a. Okay, so x minus a always appears, but x plus a only appears when n is even, 2, 4, 6, 8, etc. Okay, even integer numbers. How about x to the n plus a to the n divided by x minus a? Again, when is the remainder is 0, the remainder is evaluate the polynomial at the root, a to the n plus a to the n, right? Which is 2a to the n, and this is only 0 when a is 0. So, and it's obvious, if I divide xn divided by x, the remainder is always 0, because x divides x to the n. How about x to the n plus a to the n divided by x plus a? What is the remainder? Remainder p, evaluate the p at the root, which is minus a. And it is minus a to the n plus a to the n, a to the n minus 1 to the n plus 1. And this is only 0 if n is an odd integer. Okay, and we've seen one example, x to the cube plus a to the cube is x to the a, x plus a times x cubed x squared minus ax plus a squared. Okay, so x plus a divides x cubed plus a cubed. In each of the above cases, find the quotient of division. Yeah, we can, let's go and do the last one. X to the n plus a to the n is equal to x plus a, and n is odd. X to the n minus 1, right? And then I get a x to the n minus 1 extra, so minus a x to the n minus 2, and then I get plus a squared x to the n minus 3, and minus, so the signs alternate between plus 1 and negative 1, exactly as we wrote for the n equals 3 case, right? You start with the highest degree and then multiply by a squared, a cubed, etc., and alternate the sign one by one. Okay? Which, question 65, which one is a factor of x to the 24 minus 1? That's very interesting. X, so our polynomial is x to the 24 minus 1. Now obviously what we need to do, first of all, we factor 24. 6 by 4, 6 is 2 times 3 times 2 to the second is 3 times 2 to the third. This is factorizing 24 in terms of its primal bases, right? Or primal factors, 2 and 3, 8 times 3. All right, so x to the 8. So if I write this x to the 8, basically what I can do is make a change of variable. And let's start from the x to the 6. If I consider x to the 6 another variable u, therefore my q as a function of u is u plus 1. And if I want to see if I write the p in terms of u, it becomes u to the 4 minus 1, right? And obviously u to the 4 minus 1 divided by u plus 1, the remainder should be p of minus 1, which is 0. So x6 plus 1 definitely divides or is a factor of x to the 24 minus 1. How about x to the 4 plus 1? Let's define x to the 4 as v. And therefore my q of v is v plus 1. And p of v, so 4, 6. v of 6 minus 1. Or, yeah. Okay? And the remainder here is p of negative 1. It's still 0. So x to the 4 plus 1 is also a factor. How about x cubed? In order to do that, let's define x cubed as w. Therefore, q of w is w plus 1. And p of w is 3 to the 8th. w to the 8th minus 1, right? And the remainder then becomes p of negative 1. And it's also 0. So x3, x to the 3rd plus 1 also is a factor of x to the 24 minus 1. How about x to the 8? If I define x to the 8 and z, and then q of z becomes z plus 1, and p of z becomes z to the 3rd minus 1, and then the remainder is p to the negative 1. P at negative 1 is negative 2. So x to the 8 plus 1 is not a factor of x to the 24 minus 1. Okay, so this is the end of the polynomials. And I have some extra problems, 6 problems. And these are, again, challenge. So these are going to be hard problems. And I'm going to post the solution of these problems in a separate video. So if you want to basically not go through these, that's fine. You can skip them and move on to the next lectures. Otherwise, you can review them, and I highly recommend you try to solve them by yourself first and then review my solutions as well. Thank you for paying attention.